Hey, how's it going? Thank you for tuning into another edition of OpenPair. This is going to be a little tutorial slash study session. We're going to be talking about linear regression modeling using Python. And I only have a little bit of coffee left, so I'm going to try to squeeze as much juice out of this as I can so I can make it through because I'm tired. It's early. It's either early or late depending on where you're from, but right now it's like 6:30 a.m. So let's just try to get this done. If you watched the first video in this series, I was talking about doing the cost function of a linear regression, which is kind of like a little bit deeper into this topic. Originally, I did talk about linear regression modeling in Python, but I did it on my other Twitch channel. And then I decided I wanted to do this on YouTube so that people can come back and watch these without worrying about the videos expiring. So I'm going to try to run through this as quickly as possible while also explaining as much as possible. The caveat is that I am not an expert on machine learning. Like, I am literally studying this and learning this as I go. And I find that doing explanations, tutorials, and stuff like this kind of helps me learn. So forgive me if I stumble a little bit, but we're going to get through this hopefully just fine. So as you can see here, I have some notes that I've taken in Obsidian here. And before I get too deep into this topic, the first thing I want to do is kind of like lay out for you what is machine learning, and also turn my music down because it's kind of loud. I want to lay out for you like what is machine learning and how it's used and the different categories of machine learning, and then that will sort of set the groundwork for understanding like what a linear regression model is. And then we'll go into an example of how to model out linear regression using the Python programming language. That's a lot, but I'm going to try to keep this to an hour long, but we'll just see what happens because I don't want to do a part two of this because I've already sort of moved on myself from this topic. I have to like portion out my remaining coffee in like sips, so that was probably like a fourth of what I have left. I'm trying to like, save stuff for later on. Okay, so machine learning is a big topic. Machine learning is it's a part of this bigger picture of artificial intelligence. Machine learning is the part of artificial intelligence that allows us to basically create models that the computer can use in order to make predictions and to analyze data sets. With machine learning, there are basically two categories of machine learning, as you can see here in this section here. One is the supervised learning, and the other one is unsupervised learning. With both of these, the value of machine learning is that it allows us to basically create a programmatic way of solving problems and making predictions without having to explicitly program in like all the like nitty-gritty details of an algorithm. This is a way that the computer basically can learn on its own how to make predictions about the trends in a set of data. And this is more or less a subsection of like general statistics. So you're going to see like a lot of like math type of things here. Yeah, if you've studied physics, there might be some things that you recognize, like vectors and scalars, and plotting things on charts, and you're going to recognize some things from trigonometry and from calculus as well. At least some of the language is going to be similar. So if those are topics that are not really familiar to you, don't worry. I will try to break them down a little bit, but it's kind of good to be familiar with those things. And those are things that you could probably learn in like a week or two if you really studied. The big thing you want to understand is like how do functions work in mathematics and in programming. And then there's like some notation things like exponents and representations of indexes, arrays, stuff like that. So let's just jump into it. Linear regression is a part of supervised learning. Supervised learning is one of the categories of machine learning. And in supervised learning, you're going to provide an X and a Y. The X is like an input and the Y is an output. So basically the whole goal is to give it a training set of data where you say, for this X, you expect this Y, given some sort of model or function in between. That model or function is like basically a way to transform your X input in order to get a distinct y output. And this is generally represented on a graph, such as the one that you will see here. So hopefully you can see this. Try to zoom in a little bit. So x-axis, y-axis. X is the horizontal, y is the vertical. So for every x, we're going to be trying to get a y-coordinate, and that's based on our training set of data. And here I have, you see the little red scatter points here. There's just 2 items in my data set here that correlate to an x and a y. So 1, 300, and then 2, 500. But in a real situation, you could have many, many more, like hundreds or thousands or millions, I guess, of more things in your training data set. And the whole point is to derive some function. In this case, it's a linear function, a linear regression function, but there are other types of functions you can get that you can use to model out the trends in your data. But for this one specifically, we're talking about a linear regression. As a caveat, there's also unsupervised learning as well. That's a whole different topic that there will be videos for later on, so I won't get too deep into that topic here today. Let me get my little tabs here corrected. Okay, so the whole point of this, like I said, is to design and build machine learning systems. With real applications of machine learning, you might be taking multiple algorithms and multiple models and chain linking them together to get a really complex model. But in this case, we're just making a very simple model. And we're using X inputs mapped to Y outputs. And that is going to represent whatever like happens in that area in the middle, like the actual function to get from X to Y. That is our model. And the goal is to get a model so that we can input some unknown, some unrepresented X input and make a prediction about what the Y output of that should be. Applications of this supervised learning can be used for a lot of things. A lot of times it's like for sorting things, for speech recognition. You can use it for translation, all sorts of other things. But the big thing to know is that when you do supervised learning, you're providing examples of inputs and correct outputs, and then you're making a prediction on some new input, and then you're basically going to get a prediction about what the Y or the output of that should be. And then the integrity of your model is going to be in whether or not that prediction is correct. So the whole point of doing a regression, there's 2 types of supervised learning outcomes that you're looking for, either a regression or a classification. In a regression, you're trying to get a number from infinitely many possibilities, but these are numbers. That's the big thing to know. So numbers are going to be like 1, 2, 3, 4, some discrete set of numbers. And these numbers can be represented as not just scalars, which are just a single number, but they can also be represented as vectors too, which is like 2 numbers that are together in some collection. But you can also have like other dimensionalities of arrays too, aside from scalars. And I'll get to that in a little bit, but just as a preview for this, we're using NumPy, which is a dependency in Python that allows us to perform calculations against multi-dimensional arrays. The other way that you can do supervised learning is to create classifications. Classifications would be, for example, for that would be like telling the difference between a cat and a dog in a picture, or making a prediction as to whether or not an image or some data about the physical body is a specific diagnosis. Like you're providing basically information in order to get a prediction on what case something falls into based on whatever the input values are. So regression is a number, whereas classification is some category, some categorical prediction. So I think that's the big thing to know. Like I said, unsupervised learning is a whole different category. Right now we're just talking about supervised learning. So with that, I'm going to go to my next notes here to talk about linear regression. So linear regression, like I said, is supervised learning. This is linear regression. Linear just means like a straight line, something that follows like a straight linear progression The way to think about it is like there are nonlinear functions that you can create in like trigonometry or calculus, such as like sinusoid waves and parabolas and exponential curves and stuff like that. Those are things that you can do with more complex models and functions. But for this, we're just talking about like straight lines that have different slopes, basically. Um, and to be more specific, in this case, we're talking about univariate linear regression models. Univariate means that we're only going to have like one variable for our input in this specific example. So like I mentioned before, your inputs can actually be multi-dimensional arrays. So you could have like, instead of like a single x value, you could have like a x value that is, or x variable that represents an array of numbers. But in this case, we're just talking about one single number to keep it simple. So in linear regression modeling, the goal is to fit a straight line to accommodate or to model out some set of data that is represented on a data table. And there are other types of regressions, like I said, but in this case, we're thinking about, this is a good example. We're thinking about if we were to have like a bunch of data points, so these little red scatter points here, these represent like data that's modeled, right? So if we were to take all this data that's modeled on this plot, how could we create a linear line with some y-intercept and some slope that accurately, or as accurately as possible, represents like the general trend of this data? So that if we were to like toss in some unknown variable here, some unknown y x input, we can make a prediction about what that would potentially give us as far as a y output, which would be the prediction. And that prediction is going to have a level of error, you know, because linear is very simple. It's very much a guesstimation. There's going to be some error that we're going to also try to determine for testing and understanding the integrity of our model. And that error is going to basically represent like the difference between this line and the actual data points that are in the model itself. And it would be very rare for those two things to be the exact same, especially if you look here, these training data rows, rather, they don't necessarily fall on a straight linear line themselves. So that just means that our linear regression line can never fully represent this 100% accurately. But there are, like I said, other models that you can use that can do other cool things to better represent this set of data. When you're talking about the data set that can be used for linear regression, there are two ways that you can represent that. And side note, this is actually based on a course that I'm taking from Coursera that is provided by Deep Learning AI. So some of these images in here are from that course. Sidebar. So back to the point. So there are two ways that you can like basically represent this data set. You can represent it like on a plot here. These little X's here are scatter points represented on a XY plot. You can also represent it on a data table here. So this first column, this represents the X-axis. So here you have 2104. That would be like somewhere like right here, right? On our chart. And then this would be correlated with a y-axis, which would be 400. So this first row here would probably be somewhere like right here, right? Probably this point right here. And so for each of these, there would be some point on this plot that represents each of these data points. Hopefully that makes sense. These data points here, these are all going to be included inside of two different arrays, an array for all of the X values, an array for all of the Y. These are not just Y values, these are called Y hat values. That's the way to distinguish them from the actual predictions, because these are not predictions. These are examples these are examples that are used to make predictions. So these are Y values, but these are Y values in the sense of being examples. So these are two separate arrays, and these two arrays are basically ran through the model as variables. And then as you can see here, the person who created this tutorial, or this course rather, he made these graphics And I'll try to post the link to that course on the channel somewhere so that you can go check it out if you want to take this course. But yeah, I'm not going to use all his graphics and all of my stuff though, because I don't want to get copyright stricken or anything like that. But if you want to know, these specific images come from that. And I'm going to show you basically how you can create these diagrams like what he has created for yourself. And that's what we're going to be using Python for in today's example. So the terminology that you need to know for this is that a training set is the data that is used to train a model. A training set in this situation would be like, let me just go ahead and give you an example. A training set would be like this. So we have X training data, and that would be like some numbers like one, 2, 3, 4. And then we would have Y training data, and that would be like, let's just say 2, 4, 6, and 8. And then we would basically take this X train, and we would take, and we take this Y train, and then we would run them through some function. This is just pseudocode, by the way. We run them through some function, and then at the end of that function, we would get some model. And then what we could do with this model would be like, this model would be represented as like f of x. That's like a traditional way to represent that in math. Basically, what we could do after we create our model is that we could run f of x, where assuming that x is some number from some number that we want to make a prediction on, basically. And then from that, we would get some output, and that output is going to be our prediction. So some output prediction. So that's basically what we're doing here. We're using a training set, and remember, for every index within this X training set and every index within this Y training set, there's a correlation. So 1 is correlated to 2, 2 is correlated to 4, 3 is correlated to 6, and 4 is correlated to 8. And these represent coordinates, right? So another way to represent this would be like this. Like if we represent this as like a multi-dimensional array, it'd be like this: 2, 4, so on and so forth, right? And each of these in our data set, they would basically be coordinates that could be mapped onto a plot like this. So when you see like these little scatter points, just remember that this data table represents this first column and this second column as if they're these like training sets. The X, which is this first column here, these are the inputs. This Y is the output. The Y training set is the example, and the data set that is used to train might be thought of like this. But the whole point is that we can pass in some new X into our function, the model, and then we can get some sort of prediction that hopefully is good enough to be practical. Something else to know is the notation. There's a lot of like mathematical notation going on here. If you can see this here, this is all like done in LaTeX, which is a way to like represent like math notation and like markdown, and in some like, I guess, math applications too. But in this situation, just remember that X represents the training example, the input or the feature variable. Y represents the example output or target variable. These are both things that we explicitly pass into our machine learning algorithm, and we use these and we calibrate it essentially with weights and biases in order to determine a regression line, so that we can use that regression line and we can use that model to make a prediction. So a single XY pair, which is like this and this 2104 and 400, that would be like a single XY pair. That's a single training example. As I mentioned before, you can have multiple training examples within a data set. So for example, I shouldn't have erased it, but for example, your data set for training could be like X, it could be like 1, 2, 3, 2, 4, let's just do that. And then 3, 6. So like, let's say you have an array, right? Array or a data set that is an array, right? And this array is multidimensional, so you have like multiple indexes here. The way that you would represent these indexes in math notation is by doing this, like, this is the latex version of it, but you can see here X and what looks like an exponent. It's like an I inside of parentheses. This just represents the index. Since we're doing this in Python, Python is a zero index language. So the first item within our array from our data set here would be considered the zeroth index. And so the zeroth index for the X column and the zeroth, or for the X array rather, and the zeroth index for the Y array, together those would make the zeroth index of our pair for our data set. And we would do that for each of the items within our entire data set. That's what we would be modeling. The ith example from our data set. A specific row within the table by index. And these are the rows that I'm sort of talking about here. Each of these is a row. Okay, so let me just make a thing here. A little comment. Should have just did this when I started. Okay, so let me just Python, that way it doesn't look weird. Okay, so this is the example data set as a multi-dimensional array. Hopefully that makes sense. Okay, so like I said, in supervised learning, the models are represented as functions. These functions are created from training sets that include an input feature and an output target. And input is the X and the output is the Y. The output target for the training set is distinguished from the actual prediction by this little symbol here, which is called Y hat. The little upside down V or whatever that's called. This is called the Y hat. So X that's being somehow transformed by some function results in a output. And in the case of training, we're going to give it this X, and we're also going to give it this Y, and we're going to say, okay, we're going to give you all these examples of X's and the Y's that should be the result of these X's given some function. And this function here actually looks like this, but just to keep it simple, just think of it like this. Or you can also think of it as f of x, which I'll explain in a second here. So X is the input feature, f is the function, which might also be f of x, aka f of x. And then the y hat is the output of the model, which is an estimate or the prediction for the model itself. The whole point of this is to come up with a hypothesis. That's another way to think about the model, the hypothesis. And in linear regression, the way we're explaining this as a function is in this notation here. If you're not like super comfortable with math, don't worry. I will try to explain this, but as I mentioned before, this would be like a really good thing to become familiar with if you're going to go down the path of machine learning, because it's very like math syntax intensive. But fortunate for us, you don't need to be like an expert at calculus or trig, but this is very much statistics, if that's not something you're used to. That was another fourth of my remaining coffee, by the way. This is a big old mug for like the little sips I have in here. Okay, so the function that we use to create a linear regression line is represented here by the function of x considering a weight and a bias, which are our coefficients. Uh, and that is equal to the weight times the x input plus the bias. So like let's say that all of these are going to be numbers, by the way, but I guess they could be other things, but for this example they are going to be just numbers. So uh, let's say that our x, our input, is the number 2, right? There's going to be some coefficient w that gets multiplied by that 2, right? Let's say the coefficient for w is, for the weight w is 2 as well. So this would be 4, right? 2 times 2 is 4. And then plus a bias, and that bias is going to be a number as well. Let's say it's 2. So 2 times 2, 4, plus 2 is 6. That's how simple this is. And all of these are going to be numbers here. And you would represent them as numbers within this formula. The function f can also be written as f of x, as I mentioned here. And then if you look here on this plot here, you can see something similar to what we had up here. This is a more simple version. For every x, there's going to be some y that correlates to the input. The y is the output of the model or the prediction. And we're trying to basically create a straight line that represents the linear function that models this general pattern of this data set. So you can see here, this blue line is represented by this function that we just described. Linear just means that the way that this line goes up, you see it's like diagonal, or I guess it's this way. You see how it's like diagonally moving like this way? Well, the way that this works, it seems a little complicated, but it's pretty easy. So there's two main features that are used to represent a line here. The W here, which is the weight, represents the slope. It's the angle. It's the angle. So if you ever took trig and you know that on a triangle that's on a graph, like there is a slope. That slope is also called theta. It's the theta of the hypotenuse. That's what the weight is. The weight is like description of how this line is sloped, right? It's the progression, or maybe it's regression. I get my words mixed up. And then this B represents the y-intercept. This B represents at what point when this line is on this plot here. At what point does this line cross the y-axis as it's like starting its journey up, right? This line, by the way, could be sloped in either direction because either of these coefficients or even the x can be positive or negative. So the key things to remember is that the weight represents the slope and the bias represents the y-intercept. Just as some notes on this notation, just remember that when you see the f with this subscript w comma b, that is just a symbolic way to represent like the model as a whole, and then this x is like whatever you're passing into that model. And the actual thing that's happening with this function here is just this simple arithmetic, or I guess this would be like algebra, arithmetic or something. Like these are going to be numbers and you can just do the math pretty simply with these. The parameter of the weight and the bias. Those are things that will become easier as you do this. When I first started, it was a little confusing, but it makes more sense a lot more that you kind of just mess with it in like Python and stuff. So the result of the model evaluation at any index of the x column can be written as this formula right here. So remember earlier I was saying when you see like x with a superscript parentheses I, that's just representing one of these indexes from the column of the x-axis. It could be a number. And if we were looking at this whole thing as a multi-dimensional array, it would be like from this first index, this x coordinate. From the second index, it would be this 2. From the third index, it'd be this 3. The first one's always the x, and the second one's always the y. So that's pretty, I guess I explained that as much as possible. One of the things to think about is like how do we, once we create like a regression line for our data, this regression line is not something that is automatically generated at this point, at least. So what you're gonna be doing when you do this very simple linear regression modeling is you're gonna be trying to figure out like what's the best weight and bias so that this line gives us the best predictions for the data set that we've trained our model on. And that's like a separate problem that we can resolve using what's called a cost function. If you want to know more about cost functions, go see the first video, which really should be the second video of this series. But in that video, in that live stream video, I cover like at least the beginning of the cost function formula, and there will be multiple parts in that series. So with that said, I think I've done everything in here that we need to talk about. I have another set of notes here that we'll come back to. Sidebar, I'm a note taker, love taking notes, also love to share them, also love to share them for free. If you want to see the notes for these, there are two places you can check. If you go down to the description of this video, you can either go to my LinkedIn or you can go to my link tree. And my LinkedIn, I typically will post the notes in the form of PDF documents that you can just view directly on that website, on my profile there. Or you can go to my blog, the Matter Dev blog, matter.dev is the URL. I don't have these notes up there yet, but they will be up there at some point in the future. I just don't know when. So if you want to see these notes, like I said, you can just go check at those two places and treat them like cheat sheets. Okay, so now on to doing this in Python. Hopefully I can get through this without stumbling too much because I actually did this a couple of days ago on Twitch. Okay, so what we're doing here is we're talking about how do we represent this whole formula. The formula for modeling the linear regression line with a given data set. How do we model that, and also how do we represent the weights and the biases for these linear regression lines in a programmatic way? The first thing that we're going to do is we're going to use two dependencies for this. This NumPy, it's a library used for scientific computing. In this context, what we're using NumPy for is we're using it to create and also to perform calculations at some point in the future on a multi-dimensional arrays. Basically, it's going to take a set of data and it's going to create a like some sort of object that we can use to manipulate and whatever. For this case, it wouldn't be like really necessary because we're dealing with such a small example case. But if you're working with bigger data, you definitely want to have something like NumPy. Matplotlib is a dependency that we can use to create like charts and diagrams and basically data visualizations. And those are going to basically allow us to visually kind of see what's going on with this. And there's some styling that happens here too, but that's not really a concern right now. So these arrays represent the data set from which the algorithm will derive some model. In this case, a linear regression. I'm just going to walk through this code here. And then for each of these bits of code, there's some output that I'm also going to talk about. By the way, this is Jupyter Notebook, which is a very popular application for like both taking notes and also creating code in Python. But you can do this outside of this app if you'd like to. You can also do this with other languages. I just would recommend doing it Python since it's the most common. So this X train here, this represents our X train and Y train represents our actual data set that we're using to create our model. These are the examples of inputs that correlate to outputs. And for every input, which is the X training data, we need to have an output example as well. So that our algorithm knows like for sure that for one thing, we have another thing, right? And so these two arrays need to be the same length. And that length is going to be something that we can actually programmatically get as well. So you see here, I just created basic data structure, two arrays that have two different numbers. And what these numbers here represent, these are representing like house costs related to square footage. Where did did they go? These are like, it looks here like it's like 1 and 2, but these are actually like reduced numbers. If I go back to my regression thing here, you can see that where I have like where I have like 1 here and a 2, this represents like thousands, so it's like 1,000, 2,000. But you know, since this is math, we can like actually divide these by 1,000 to get smaller integers, I guess. And then where it says 300 and 500, these are thousands as well. So this is like I'm sorry, these represent dollars. So where it says 300, this is like $300,000. Where it says 500, this is like $500,000. But for the purpose of this, we're just treating them as smaller numbers. Okay, so for this next part here, these arrays for the X training data set, column of our data set, and the Y column of our data set, they are represented by, the length is represented by some variable that we're going to just call M. M is the size of our data set pairs. In Python, there's 2 ways that you can get these sizes for the arrays. One way that you can do it is by calling dot shape on your NumPy array, and that's going to give you a number. In this case, it's going to be 2. Another way you can do this is by calling length, which is just like a built-in method in Python, and it's going to give you the same thing. The difference, I guess, is that this dot shape is something that's coming from NumPy. It's like a method, and then from NumPy, and it's like Python. I think there might be some performance implications from doing one or the other. I don't know the exact answer to that, or like the exact best practices for that. So don't quote me, but for this, we're just going to assume that we're going to use this dot shape. Dot shape, just remember with this that when you call it dot shape, you need to pass in this 0 here like this, because if you don't do that, then okay, let me back up. Since NumPy is kind of built to work with multi-dimensional arrays, when you call dot shape, that doesn't really say much about the dimensionality of the array that you're trying to get a length for, like which of those dimensions. So we say 0 here because we're just going to say, like, regardless of the size of this multi-dimensional array, we're just only going to consider the first dimension, because in reality, these rows for like the X column, it could be like 1 comma something else. It could be like 2 comma something else. It really could be any size, but we're just saying that we're going to use the 0th index, or the 0th index for dimensionality here. So it might seem a little arbitrary, but that's kind of necessary for using the NumPy method shape. Whereas if you were doing just length, the len method here that's like built into Python, you wouldn't need to like do anything weird like that. So just remember, like when you're doing this dot shape method, that you got to pass in this 0 here. So those do the same thing. So as I mentioned before, when you have like your columns within your data set, which is in my example over here, each of these rows, these XY pairs, they represent like an index, you can say, if these were considered like this, right? They would represent like indexes. But in like math notation, what we're just basically saying is like for the whatever indexed pair, we're going to couple those together. So for X at the 0th index, it'll be, for this example, it'd be 2104. For Y at the 0th index, it'd be 400. And these indexes are going to follow the entire length of this array. And these 2 arrays for the X and the Y are the same length. So in this example that I'm doing in my code here, what we've done is we've created a set of data where the X training data is 1, 2, and the Y training data is 300, 500. So the 0th index of x and y is going to be 1 and 300. And for the first index, it's going to be y. It's going to be 2 and 500. I think I mentioned this before, but Python is a 0-indexed language. So the 0th index is actually the first, and the first index is actually the second. Some languages are not 0-indexed, but Python is. These indexes here can be symbolically represented as I, which can be a variable, because what we're going to do is we're going to iterate over them, and we're going to like pass in, we're going to use like a loop to iterate over this when we perform our modeling. And so we need this index to be able to change so that we can actually perform these calculations over the entirety of our data set in order to get that linear regression line. And then later on to do our cost function as well. So here you can see that the index is going to start at 0 for our model, and then we're going to iterate up from there. So x at whatever index is going to be x training or x train, and then we're going to pass in our variable, and then the same thing for y. And then you can see here that when we do this without doing any iteration, any looping over it, it's just going to be, this right here, basically. It's going to evaluate to this. And if we were to change this to 1, then, we would get our second set of numbers, which would be 2 and 500. I'm going to run that real quickly so you can see. So 2 and 500. I'm going to go back to 0, though. Don't want to mess anything up. Okay, so the next thing we want to do after we create our training data, the correlations between the x and the y, is we're going to actually plot this out on a chart, on a diagram. I don't know, like what's the difference between a chart, plot, and diagram? I don't know. We're just going to call it a plot. That's the okay, I don't know what that means. We're just gonna call it a plot for the time being. Okay, so these little red X's here, they look like big old chunky dots. These big old like little X's here, these represent scatter points. And you can see here, we're using matplotlib to create scatter points. And we're gonna pass in our X and our Y coordinate here, our coordinates. And we're gonna style them to be these X's, and they're gonna be the color red. So marker is what the actual point looks like, the scatter point looks like on our plot here. And then this C is just a way to configure the color. R is red. And then we have a label here. We have a title for our plot, housing prices. And then we also have a label for each of the axi. And then this dot show is basically just calling the rendering so that Jupyter Notebook can show us this graphically. Okay, so to model this function, what that means is like we're going to actually create an algorithm here that will allow us to iterate over all of these variables so that we can get an array at the end of all of this that represents our actual model. And then that model is going to be something we can use to pass in some unknown X input, and then hopefully get a prediction for what the Y of that unknown X input could be. The way that we do this is with this formula involves setting a weight and a bias, and that weight and a bias is what allows us to get this linear line. If you remember here, I was saying that the function of a linear regression is the function of this linear regression is the weight times the X input plus the bias. Here we're just going to use 100, and we're going to use 100 for the weight and 100 for the bias. And then just printing this out here so I can see it. I think it's always good to, when you're doing things like this, to print them out so you can visually see it as output. So let me zoom out a little bit so you can see all this. Took some extra notes here too. Let me break this up so it's easier to read. Okay, so this is going to be a function here where this function represents all the stuff that needs to happen in order to get a an algorithm that's going to hopefully perform some type of prediction. And for this function to work, we need to pass in our x input, our weight, and our bias. It says here this computes the prediction of a linear model. And here's some description of what these different arguments, how they're defined and what they mean. So x is the data, and there are m number of examples of x. M represents the length or the number of items within that data set that are delineated by some index. WB is a scalar value. Model parameters, they can also be called coefficients if you're talking about this in terms of math. And these are our weights. And then Y is the target values. Y represents like the target values that are the actual things that correlate to our inputs. These are the things that we've used as examples of what this algorithm hopefully is using to determine like what is the correct output given some x. So as I was saying before, x dot shape at the 0th index for that array's dimensionality is going to be the length. And then you see here it says f underscore WB. All this means is that we're creating an array that is full of zeros that has the same size as our x data set. So down here I just have some in my comments here. I have if our data set, for example, is like an array of 1, 2, 3, and 4, this array's length is going to be 4. So x dot shape with this 0 here being passed in, that is going to be the number 4. That is the length of our example array here, right? And this is what it's literally creating here. It's just creating like an array with 0, 0, 0, 0. And basically what we're doing is we're creating like a data structure. We're reserving some capacity in memory so that we can transmute this. So this is not functional, or what's the word for that? This is mutable. This is like a mutable data structure. So this is not like a functional style. This is like creating an object, and then essentially this is like creating some type of object data structure dictionary thing that has like placeholder values, and then our algorithm is going to iterate over each of these indexes, and it's going to perform the calculation and then replace these zeros with some new number that represents like, you know, the output of our training set, which is the collection of y values, or, you know, some y's given certain x's. So this is our loop. This is the loop that's going to take the length. It's going to take for every index within the size of our data set. So here, for every index, we're going to perform this calculation where we pass in this variable I, you know, so where it says f underscore WB, it's saying for whatever index we're on in this iteration, we're going to take the weight and the bias, which are static values for the duration of this function, and we're going to multiply the weight by whatever the x is at this current index, and we're going to add our bias to it. And then after we do this entire iteration, this entire looping process, we're going to return the new replacement collection that will overwrite this initial collection of zeros. So to kind of paraphrase that, this loop will create an array of zeros that is the length of our input array. Each iteration of the loop will replace the corresponding index with the calculated value from the model. That's a simple way to explain that. The temporary variable for the model output, that is like a placeholder. Another way to think about this temporary variable, which is this temp underscore f underscore WB, that's just essentially our y hat. So I was saying here before that we have y hat, which represents the actual output of the model. That is what this temporary f a function of x, considering WB represents. And so you can see here, these are the arguments that we're passing in to this compute model output. We're just holding it in this variable. What I did here is I actually printed out each of the components of this so that I can easily see when I create my plot here, I can see how this plot was constructed. By the way, sidebar, when we're running this model to create the linear regression, and also when we're displaying our data set, we're kind of just using the same X column in both scenarios. So the math here is pretty easy to do. We'll go over that as we get to it. To kind of explain this code here, we're just creating another. This code here is to create this plot here, down here. And just to kind of explain how this works. So with our plot, these first two arguments for a plot represents X and Y. These can be arrays, which in this case they are. X train, remember, represents our points for along the X axis. And then instead of using the Y train, we're actually using the modeled output here. So this is a collection of X coordinates essentially, and then a collection of Y coordinates, and they're going to give us different different points that define our regression line. And then these are the labels and the color configurations, and that's how we're getting this blue line here. Basically, this is the depiction of our regression line. And then the second part here, similar to before, these are just the scatter points, which in this case we just have two. We only have two sets of XY coordinates that we are using for our training data set. And then you can see here, there's a difference between our linear regression line and our actual data set. And we're going to talk about that in the other video, the one for cost function, because there's a way to actually map this regression line more accurately to our data. But that's not the point of this video. So these are just labels and titles and stuff. Remember that the title is the title for the entire plot. The labels that correspond to X and Y are going to go here and here. So plot.y label, plot.x label. This legend method here is basically going to take the X label and the Y label, and it's going to put them up in the corner. I think there's some configurations you can do to like move this around and stuff, but for now it's just here. And then this plot.show is what actually renders our plot here. So a linear regression line will always give a line that goes through the X input and the Y training output pairs. The input data and the output of the model. Remember, Y hat is the output of the model, and then the actual plain Y is the prediction given some unknown or some novel X inputs. So the goal in all of this is, well, there's two goals. One goal is to create the line, and the second goal is to make sure that the line is the best line that fits our data. And in order to get a line that fits the data well, you need to configure or to calibrate, I don't know if like a better word, but you need to determine what the best weight and bias are. And the weight and the bias is going to have an influence over the slope. So the slope is how like diagonal. Ooh, excuse me, I just burped. The Y, the W, the weight is going to determine the slope of the line, you know, how like diagonal it is, and the bias is going to determine the y-intercept. So at what point for every x along this x-axis, at what point does this initially cross the y-axis? So that's what the weights and the bias are going to determine. So here's an example of making a prediction using the model. So if we're predicting like the price of the house in correlation to our training data, we're going to basically just have to configure or change like this weight and this bias in order to figure out like how do we create the best model. Once we create our model, once these weights and these biases are fixed, then the expectation is that we can pass in some new X value that isn't necessarily represented in our training set. And based on that training set, we'll be able to make a prediction that has some degree of integrity so that we can use it to determine, like, you know, the outcome of some new value. So for example, remember these are in these numbers here are like in reality in the thousands. So like if we were to say like 1,200 square feet pass into the model that we created, then that house value would be $340,000. If we were to change this to 2,000 or yeah 2,000 square feet, then it'd be $500,000. And so that's kind of the point of this whole thing is to and by the way, we're doing this only for one X input, but in reality, we would actually be able to perform this iteratively, looping over an entire set of some fictional or some novel set of X input data, and we'd be able to get like multiple numbers here. And you can do this with any set of data that has XY pairs. And that's kind of the cool thing you can do with linear regression modeling. So that was a lot. I feel like that was a lot. That was really fast. Like I said, I will post these notes for you to look at on my blog. Hopefully they'll be up soon. If you want to have like updates about when these notes go up and stuff, for the time being, just go ahead and follow me on LinkedIn. The links are down in the description of this video. You can also check out my blog, matter.dev. The same name I use for pretty much everything. Matter.dev is just my go-to name for all this kind of stuff. So if you want to know when these notes go up, just follow me on LinkedIn, or you could just check the blog and see. I'll try to have them up hopefully by the end of the week. And then the next thing after you create your model, as I mentioned a couple times, is you have to figure out like, okay, now that we have this linear regression charted out here, what should the weight and what should the bias be so that we can get the best line here? And that's like a whole separate problem. But the way that that's solved is by performing what's called a cost function. And the cost function is the way of analyzing this regression line to figure out like what is the degree of error that you're likely to get whenever you're making a prediction with your new inputs. And that's because like when you're making like a prediction using machine learning, it's never going to be 100%, but the more complicated your model is, and also the more uniform your data is, the better your predictions are going to be. And that integrity is it's described by a number called the cost. If you want to learn more about that, all you have to do is go to the very first video in this series where I'm kind of describing that, and then I'll post more videos about that here coming up after this video goes up. So anyways, thanks for checking this out. I know this was like a long stream. It was long for me. Also, I'm tired. And I have like 2/4 of my coffee left. I'm going to go ahead and drink that right now. And I'll let you go. Thanks for coming by. Peace.